Alright, welcome guys. So we have this question here that says we need to prove this by mathematical induction here. Alright, so step number 1 here is that we need to show that the statement is true when n is equals to 1 here. So what we do here is we get this, we equate it to what we have on the right hand side here. So that's n cubed is equal to, open brackets, n plus 1 divided by 2 to the power 2 here. So where there's n, we substitute with 1. We're going to have 1 cubed is equal to 1 open brackets 1 plus 1 here divided by 2 here. So let me just write that one nicely. Alright, so here 1 plus 1 like this here, then everything to the power 2 here. Then here 1 to the power 3 is equal to, so 1 plus 1 I'm going to get 2 multiplied by 1, we're just going to have 2 over 2 the power 2 here. So here 1 to the power 3, then here we're going to have 2 into 2 1 squared here, so 1 here is equal to 1 here. So if this is the case, then we say therefore true for n equal to 1 here. Alright, let's go to the next step, which is the inductive hypothesis. So let me just do this here. Alright, so we go to step 2, which is the inductive hypothesis. So here we make an assumption that we assume that it's true for, so assume that it's true for n equals to k here. So mean that where there's n, we just substitute with k. It is the only thing that we get to do under the inductive hypothesis. So 1 cubed, 2 cubed, 3 cubed, plus up to the k term. So k cubed equal to, open brackets, k plus 1, oh sorry, so here alright, so here we have k plus 1 divided by 2 here, and we have our power to the side here. So this is the only thing that we get to do under the inductive hypothesis there. Then we go to step 3. So step number 3 now, we show that it's also true for n equals to k plus 1. So meaning that if we add the new term to the already existing terms here, the statement that we have should still remain true then. So meaning that here we're going to have 1 cubed plus 2 cubed plus 3 cubed plus the k term here, plus now if this is the k term here, n equals to k, then we also need a term for n equals to k plus 1. So meaning that where there's n, we substitute with k plus 1. So we're going to have k plus 1 to the power 3 is equal to, open brackets, on the right hand side here, where there's n there, we substitute with k plus 1. So we're going to have k plus 1, open brackets, k plus 1 plus 1 the power, or divided by 2 here, and everything the power 2 here, like this here. Now, starting from the first term here up to the k term, these terms here, they give us the left hand side of the inductive hypothesis here, meaning that where there are these terms here, we can just substitute with this here. So we're going to have k, open brackets, k plus 1 divided by 2, then everything here, the power 2 here, plus this term here, which is the k plus 1 term. So k plus 1, the power 3 here, equal to k plus 1. Then here we're going to have k plus 2 there, divided by 2 to the power 2 like this here. Okay. Now our goal here is to show that the left hand side is equal to the right hand side here. So if we want, we can just expand what we have. So this is the approach that I use here. So if you have a over b to the power 2 here, this is the same as a squared over b squared here. Again, if you have am to the power, let's say 2, this is the same as a to the power 2 m to the power 2 here. Okay, so now I'll distribute these powers here that we have here across the terms that we have inside the brackets here. So I mean that there we're going to have k squared open brackets k plus 1 squared divided by 2 squared, we're going to get a 4, plus here k plus 1 the power 3. So the power 3 here, let me erase that. Okay, so k plus 1 to the power 3 here is equal to k plus 1 squared k plus 2 squared divided by 4 like this here. Alright, so here I'll just write this side where there's space to solve this. Okay, so here we have k squared open brackets k plus 1 squared divided by 4, plus here we have k plus 1 to the power 3 is equal to, so we have k plus 1 squared k plus 2 squared divided by 4 here. Alright, so we make what we have on the left hand side a single fraction. So when we do this here, we're going to have 4 as the common denominator there. Then this is the same as over 1. So we're going to have k squared this side because 4 into 4 is 1 times what we have there. So k plus 1 squared plus, then this side 1 into 4, we get 4 multiplied by that, we're going to have 4 open brackets k plus 1 to the power 3 here. Okay, now when you look at these terms that you have here, you notice one thing that, let me just write this side, then I explain that. Like this here. When you look at these two terms that we have on top here, k plus 1 squared is common, so meaning that we can just factor it out there. So we're going to have k plus 1 squared open brackets here, we're left with k this side squared plus 4 open brackets k plus 1 like this here, and we close everything here, we divide by 4 equal to this side k plus 1 squared k plus 2 squared divided by 4 like this. Okay, so then we simplify what we have inside the brackets here. So we have our k plus 1 squared open brackets, there we're going to have k squared plus 4k plus 4 divided by 4 here being equal to k plus 1 squared open brackets k plus 2 squared divided by 4 like this here. Alright, run out of space again, we'll just continue from here. Alright, so here I'll do this like that there, then I continue. Alright, So here now we have k squared, or k plus 1 rather. So k plus 1 squared. So we have k plus 1 squared here. Now, if you look at what you have inside here, you notice to say that this is a quadratic expression that you have there. So mean that our product there is 4. Our sum is 4. Two numbers you can multiply to get 4. 2 and 4. You add, you're going to get 4 there. So mean that this here can be written as k squared plus 2k plus 2k plus 4 divided by 4. Okay, so we equate it to what we have on the right hand side, which is a k squared, or k plus 1 squared, k plus 2 squared divided by 4, like this here. So in these brackets that we have on the numerator on the left hand side here, so you notice that between the first two terms here that we have k is common. So we continue, k plus 1 squared, open brackets, so k is common there. We have k plus 2. Then here 2 is common, so we're going to say plus 2, open brackets, k plus 2 there. We close everything divided by 4. We equate it to what we have this side, k plus 1 squared, k plus 2 squared divided by 4 here. Then now we have k plus 1 squared, open brackets, k plus 2, k plus 2 here divided by 4 equal to k plus 1 squared and k plus 2 squared divided by 4 here. Now this here, k plus 2 and k plus 2 are just one and the same thing here. Remember, if you multiply a times a, you're simply just going to get a squared, because this is one and the same thing that you're multiplying by itself twice here. So mean that if we do the same here, we're simply just going to have k plus 1 squared, k plus 2 squared divided by 4 is equal to k plus 1 squared, k plus 2 squared divided by 4 here. Okay, so there we have it. The left hand side is equal to the right hand side here. Now, if you want to simplify this further, you not say that this 4 squared is this 4 is the same as 2 squared, and what you have this side is the same as that. So mean that here, if you want to simplify the expressions further, what you can just do there is you have open brackets, k plus 1, k plus 2 divided by 2. The power 2 here is equals to the same thing this side, k plus 1, k plus 2 divided by 2, the power 2 here. Alright, so therefore here you can just say, therefore this is true for n equals to k plus 1. If this is true for n equals to k plus 1, then the statement that we have holds under mathematical induction.